Good afternoon, AP Stats. This is kind of the timeline I think we're going to be going with from now on. I'm going to post some sort of a video every day. Hopefully, they'll get more detailed and a little better as we go. So, one of the things I did this morning was I watched the lesson on chi-square tests that AP put out today. If you didn't see that, I really hope that you'll do that from now on. What they're doing now, if you didn't see the video, is they're completing the rest of the class. I talked yesterday's video about how we're going to be testing on units 1 through 7, which included everything about hypothesis testing and intervals, confidence intervals. So chapters 8 and, or excuse me, units 8 and unit 9, according to AP, is chi-square tests and then tests for regression. That's unit 8 and 9. That's what they're doing for the next week. So for today, tomorrow, Friday, and then all next week, they're going to be going over that curriculum. I think it's incredibly important that you learn that material, even though we're not going to be tested on it. So I would highly suggest that you do that. The rest of the time, they're going to do a video every day, is they're going to be going over the review. And I think hearing another voice besides me for that review will really help a lot of you. Some of you guys didn't catch it the first time. Maybe I wasn't able to explain it the way that you needed me to explain it. Um, the review will really, really help you. I watched the video today and I was very impressed with the knowledge. And I agree 100% with everything he said about the AP or the testing for chi-square. So I'm very excited to see how that goes. I'm going to be watching those videos when they come up 11:45 every day. So that's a stamp. You'll hear my video every day after that, and hopefully you'll have seen it as well. If you don't see it, don't have access to it, can't figure out where it is, when you go on to AP Central, there's this button that says "Look how we're supporting schools," and that will get you to um, the pages that we need to go to. Okay, and so that would get you to here, and tells all the things AP is doing and the free remote learning resources. We can go to that, and it goes by class. And then, of course, we can go to statistics. And that's the page that you'd go to on YouTube to access the videos. Now, this first video is the one that was this morning, so it's already posted. Tomorrow's will come out at 11 o'clock, and it will be live from 11 to 11:45, but all of these will be posted there. Also, when you look at each of these videos, um, you're going to see, where was I? Another way to get to them, I'm going to post this in today's lesson. So if you would just want to have a quick way to get there, this gets you to that page, and then this gets you to today's lesson, to today's video. And we're back to that same page. So let's click on today's. I'm not going to play it, of course. And he started playing with it there. If you look under the description, there's another place that he said to look for, and be this um, website. You can look at that website every day and know that all the videos will be posted there after they go live on YouTube. Okay, so if you can't see it live, you might be able to see it there. I would go through the page that I had earlier, this page, if you want to see what they are live every day. So I'm going to put a copy of that in today's lesson. All right, talking about today's lesson, we'll transition to that. I want to go over the answers for the alternate examples that I gave to you guys for section 9.1. I posted this yesterday. I really think you should spend some time trying to go through these instead of watching me do the examples. But in any case, let's just go through them. So, U.S. Bureau of Labor Statistics estimates 69.7% of high school graduates enroll in a college or university. This is a population parameter, a population proportion. Okay, but that's all high school graduates. Okay, now Bernard has great pride in the quality of his large high school. He thinks the proportion of college-bound students in his high school is greater for last year's graduating class. So he thinks that his high school graduating class is going to have a bigger number, bigger proportion than 69.7%. So we want to test that hypothesis. So what we would do is we'd have our hypothesis null and our hypothesis alternate. So our null hypothesis and our alternate hypothesis. Okay, H of 0 and H of A, or H of O. Okay, so Bernard thinks that his high school's proportion will be larger than that. So the proportion that he thinks his high school will be larger than is 0.697. So what we're going to do is we're going to set up a test where P equals 0.697. And the alternate hypothesis that Bernard hopes to find information for is going to be P is greater than 0.697. Now, sometimes we get really confused on what the population we're talking about. This P has to be defined. This P is the population proportion of last year's graduating class. So P equals the true population proportion of last year's graduating class. And then it names the high school, so let's name the high school too. At, what was it? I don't think it named his high school. So his graduating class, okay? So the population that we're trying to run a test on is just the population of graduating seniors at his high school. So he got the 69.7 from the population, a bigger population, but he thinks that the population of his high school graduating class is going to be larger than that. So he wrote an alternate hypothesis for P is greater than 0.697. He's going to try to find information that supports the alternate hypothesis because he thinks this is actually true, but we're going to test the null hypothesis and see if we can find information against that. Okay, so that is the first example. All right, the second example talks about the exact same thing. It's part 2. So he just adds on to that. And so you've got P equals 0.697, P is greater than 0.697, which is what we did in that first problem. P is the true proportion of all last year's graduates at Bernard's school, okay, named his school as his school, enroll in the college or university. Bernard asks a random sample of 40 graduates from last year's, 40 of last year's graduates from his high school, if they're enrolled in a college or university, and 34 say yes. The sample proportion enrolled in a college or university is P hat. Okay, so P hat is 34 over 40 equals 0.85. Bernard performed a significance test and obtained a p-value of 0.018. All right. It says explain what it would mean for a null hypothesis to be true in the setting. Well, that means the true population proportion of Bernard School, Bernard's high school, last year's graduating class, that went to college is 0.697. So that's, if the null hypothesis was true, then that would be true. The true population proportion of Bernard's high school, last year's graduating class, they ended up going to college, was actually 0.697. They did a sample of only 40 kids. It's a large high school. So that sample of 40 kids does not represent all of the graduating class. It is a sample. So you have P, which is a population parameter, and you have P hat, which is a sample statistic. You cannot mix those up. The sample statistic is going to help us find a p-value when we actually do this questions. They won't be done. It won't be done for you. Okay. All right. So this p-value, that's interpret the p-value. The Bernard performed a significance test and obtained a p-value of 0.018. That's like putting things on a normal distribution and coming up with something that's so rare that it only would happen 0.018 or 1.8% of the time. And so that's basically what just happened there. That's the p-value. What happened is that this distribution has a center at 0.697. That is the population proportion, P. Don't confuse that with a p-value. Population proportion is 0.697. If that was actually true, then obtaining a p-hat value of 0.85, which is right there, now we'd look that up on the table, and we'd find a p-value that the area in that tail is only 0.018. That's rare. And so the theory here would be that it happened so rarely, it's probably not going to be happening by chance alone. Okay? So the probability of having a sample statistic this high, if the true population proportion is 0.697, having a sample statistic of 0.85 is so much different that we have evidence now to think that P really isn't 0.697. We would reject this 0.697 and say there's evidence to prove that the real, we would have evidence to prove against this, and now for the alternate hypothesis, now that the true population proportion is greater than 0.697. Okay, so if we interpret the p-value alone, basically it says, assuming the proportion of last year's graduates who enroll in college is 0.697, there is a 0.018 probability of getting a sample proportion of 0.85 or greater. That's why we shade in the rest of the tail. The boundary is at 0.85, the tail and forward, so the shaded area is greater. And this is or just by chance. So by chance alone, probability of getting a sample statistic that p hat that high is only going to happen 0.018, the probability. So 1.8% of the time. That's really high. Or excuse me, that's really low. All right. So that's that question. Let's move on to the next question. It was alternate example from page 559. And we go to this as a new subject of this question. So, again, you should have this, and should have already tried these problems. Police department in a certain city is trying to determine if it's worth the cost to install a speed sensor and traffic camera. We're going to collectively call that speed controls on a highway near the city. They will install the speed sensor and the traffic camera if convinced that more than 20% of the cars are speeding. The police department selects a random sample of 100 cars on the highway, measures their speed, and finds that 28% of the 100 cars are speeding. Significance test is performed using the hypothesis. Okay, so again, we have a hypothesis that the proportion of speeders is 0.20, and they're going to run a test that they think the proportion is really greater than 0.20. Okay? P is the true proportion of all cars on the highway that are speeding. The resulting p-value is 0.023. I want to show you how they got that because it's important for the do part of our full hypothesis test. So I want to show how to do that. And then what conclusion would you make at the alpha equals 0.05 level? So now we've got the alpha equals 0.05 level. That is the level of significance. Okay? 0.05. All right. So what we have here so we have another one-sided, okay, proportion test. So the mean is going to be right here. And then somewhere out here, I got to put the p-value, 0.023. Well, I don't know what, I just got the p-value of 0.023. I don't have any of the other information, but I'm going to show you how they got that. take a step back, go on to this problem real quick. We'll remember how to do this problem. I have a mean of I don't know, say 7, and a standard deviation of 1. So the first standard deviation would be at 6, the second standard deviation would be at 5. Okay, I want to find a z-score for an x value of 4.8. So I know it's going to be more than 2 standard deviations away, but I need to find my z-score with this formula, x minus x bar over the standard deviation. So the x is 4.8 minus x bar, which is 7, over the standard deviation, which is 1. So my z-score is going to be negative 2.2. And then we got a p-value when I look at negative 2.2. We'll go ahead and look at our z-table. Negative 2.2. Of course, everything we're doing here can be done by technology. Negative 2.200, 0.139, 0.0139. Okay? And so we know that that is 4.8. That gives me a z-score, negative 2.2. And then we can look up the p-value for that z-score, 0.0139. We've done that. We've done that. That basically tells you what's the probability that you're going to get a score at 4.8 or lower. P-value is 0.0139. And that's what we want to do with inference. Our formulas for our test statistics are always in this form. We're actually finding a z, which is, we're going to call that now a test statistic. And all the tests pretty much have that same thing. And then you're going to have the mean, excuse me, your data value minus your mean divided by your standard deviation. So hopefully you remember that problem. And let's go back to the problem that's at hand. I wish I was as sophisticated with all the neat little graphics that I know that AP is going to come up with. Not yet adept at that yet, so bear with me. Anyway, we're back on the example, page 559. We want to have the p-value. We're given the p-value, okay? Well, the formula that this comes from is the formula that we're going to introduce for your test statistic for this type of problem. And so if we look at your green sheet, this is a test for a population proportion. We've got p equaling 0.20. So 0.20 is basically our null value for our proportion. And then we're going to say that that's going to be greater than p sub 0. Okay? So we've got these top two. It's always the top one and then one of the alternates. All right? And then we've got a formula. There's our z. Here's our data value. Here's hypothesized proportion. And then in the underneath here, so that's like your x minus your x bar. And this down here is your standard deviation. If you remember back in chapter 7, this was the standard deviation of our sampling distribution. We use p sub 0, whatever we got here. In this case, it's going to be 0.20 in this, because we know what it is. When we looked first at the confidence intervals, we used p hat here because we knew what p hat was. The only thing we did was that we knew p hat and we were estimating what our true population proportion was. Well, now we've hypothesized what it is, so we've got that too. So this is what we use for the denominator. So then this formula, our test statistic, is p hat minus our hypothesized p divided by the square root of our hypothesized p times 1 minus our hypothesized p divided by our sample size. Okay? Now that denominator in total is our standard deviation. So in this problem, we've got a p hat of 34 out of 40. 34 out of 40 in that random, oh, whoops, no we don't. Wrong problem. What am I doing? Try again. This was out of 100. I'm sorry for that. Our p hat was 28 out of 100. Sorry about that. Look, 28 out of 100. So our p hat is 0.28. So let's take a look at that p hat. The hypothesized proportion of speeders is 0.20. Our sample statistic, or sample, says it's 0.28. So we have evidence right now to think that maybe the 0.20 is too low because our sample is much higher than what we hypothesized. Okay? So far, so good. This direction is looking good right now. So what we do to find our z-score is we put the 0.28 minus our hypothesized p, which is 0.20, and then we divide by that. 0.20 times 0.80, that's 1 minus 0.20, over 100. Okay, and I'm going to do that, just that calculation and show you what the denominator is, because that's going to be important. So 0.20 times 0.80 divided by 100, and then I'm going to take the square root of that. I'm going to raise it to the half power. That's 0.04. So our standard deviation is 0.04. And then we've got on the top there, 0.28 minus 0.20 is 0.08. And that ends up being exactly 2. Okay, so my z-score is 2. That's exactly 2 standard deviations above my mean. So 0.28 is right here. And that must mean that 0.24 is right there. Okay, so 0.20, a standard deviation of 0.04, 0.20 plus 0.04, 0.24, plus another 0.04, 0.28. So that's where my test statistic lands. Now we have to figure out what to do with that. Well, we got to find our p-value. Well, to find our p-value, we look on our z-table. What is the p-value for a z-value of 2? Well, our z-value of 2 gets us to 0.9772. This gives us 0.9772 when we look it up on the table. I'm going to zoom in on that a little bit. This z value is 0.9772, but remember, that's the area to the left, 0.9772. That's the area to the left of that. We want to find the area in the tail. And so that's going to be 1 minus 0.9772. Okay? It's 0.0028. 0.0228. That's the area that's in this tail. Okay. Now remember, at the beginning of the problem, our alpha value was set at 0.05. And the conclusion that you need to make is at a significance level of 0.05, what did the test statistic tell us? Well, it tells us that this sample of 0.28 is so high that our hypothesized value of 0.20 might be a little too low. And the reason we know this is because this area above the 0.28 is only, the probability of that is only going to happen 0.0228 times, or 2.28% of the time. Our alpha value is 5%. Okay? So when our p-value is less than our stated alpha value, we know that the chances of having a sample statistic so far from the mean is so low that now we know our mean is probably incorrect. Okay? So basically what just happened is we are going to reject that this is true, and we're going to find evidence for the alternate hypothesis. So, to be exact, because the p-value of 0.0228 is less than our alpha value, which equals 0.05, we reject the null hypothesis. That's our decision. Now we have to back that up with something in context. We have convincing evidence that the true population proportion of all cars on the highway, that speed is greater than 0.20. Now, we didn't say it's 0.28. That's what our sample said. The population proportion is not going to match our sample statistic. All we can do on this is to say that what we think the population proportion is at 0.20, we have found evidence that that's too low, because this happens so rarely to get a sample statistic so much different from the 0.20 that the 0.20 has to be wrong. That's all that we can say. So remember, our two conclusions are we reject the null hypothesis or we fail to reject the null hypothesis. Now, I talked to you guys about this area, and I called it the rejection region. That's at 0.05. So when I increase the area of this tail all the way up to 0.05, any z-value, any test statistic that ends up inside that rejection area, then we reject the null hypothesis. If it ends on the other side, for example, if the test statistic, instead of giving us 2 standard deviations, it gave us 1.1 standard deviations, which would be right there. That would fall outside the rejection region, and we would fail to reject because that would be close enough to the mean that it wouldn't happen rarely. This happens so far from the mean that it doesn't happen very often, and since it can't happen very often, then we're thinking that this p-value or this population proportion is not true. Hope that makes sense. We're going to go through more examples until it does make sense, but that's what we're going to deal with for now. Okay. We have one last question from the homework, from the homework from yesterday, and it dealt with the type 1 and type 2 errors. Again, this is one of the huge misunderstandings from this chapter. So I'm going to draw our box, and I'm going to make it specific for this particular problem. Okay, so the box that we see always has where the null hypothesis is true and the alternate hypothesis is true. And then our conclusion, we reject the null hypothesis and we fail to reject the null hypothesis. Okay, that's always the heading. So let's kind of go through these. Okay, the situation that we just had, we pretty much figured out that the alternate hypothesis was true, that the speeding happened more often than the 0.20 proportion. And so what we did is that we rejected the null hypothesis because the alternate hypothesis was true. So that's a correct decision. That's exactly what we did on the last problem. Okay? If we had found that, I'll go back to the graph real quick here. If we had found this was the correct spot, that would only be 1.1 standard deviations above the mean. Maybe that's somewhere in the, it happened, 20% of the time, for example. Okay. 20% to the left. Actually, it couldn't be 20%. That would be something like 12%. 12% here, only 12% of the curves to the right of there. Okay. So if we found it here, it wouldn't be in the rejection region, so we'd fail to reject. And that means the null hypothesis would be true. So if we fail to reject when the null hypothesis is true, that is also a correct decision. The one that we made was the upper right. But if we'd found different test statistic, the possibility is that we would have made this decision. Okay? Now, the other two are the errors. We have an error because maybe our test statistic was done, but our sample was really different from most samples. So we could get a sample that is inside the rejection area, okay, inside the rejection area, but the null hypothesis is actually true. This is a type 1 error. We could actually have this be true and still get a test statistic way over here because our sample was, it's in the 5% of samples that would actually end up here, okay? Who knows? Maybe our sample is wildly off from what it should be. Maybe there's a drag race going on at that time, and there's a whole bunch of cars that came through that were speeding, okay? And that's really not what the true population proportion is. There's all kinds of reasons why this sample could be off. And it's going to be off a little bit of time. So there's going to be an error there. And the error that we reject in is 5%. So anything that ends up here that really the null hypothesis is true, that's a type 1 error. And that's tied to alpha. Whatever alpha is, that's the population of a type 1 error, or the probability of a type 1 error. The other error that we get is when we should reject the null hypothesis, but we fail to do it. Okay, so that is a type 2 error. Okay, so on this particular problem, a type 1 error. This is where the speeding proportion is actually 0.20. That means the null hypothesis is true. But is incorrectly rejected. Maybe we get a sample that tells us to reject it. Now, what the problem is when that comes, and the problem says, describe a type 1 error and a type 2 error in the setting and give a possible consequence of each. So type 1 error is the speeding proportion is actually 0.20, but it's incorrectly rejected. And the consequence is the police department wastes money on speed control. So it would be the camera and the traffic camera and the speed sensor. We call those speed controls. The police department wastes money on speed controls when it wasn't necessary. In the scheme of things, that's not a terrible thing. You're wasting a little bit of money. No, we don't want to waste a whole bunch of money, especially tax money, but nobody's life is being put in danger on this type 1 error. So not a big deal. Type 2 error, and it'll change by problem the seriousness of the errors. Type 2 error is when we fail to reject, but the alternative hypothesis is actually true. So the speeding proportion, my cat's going crazy there. Hopefully you can't really hear it that back in the background. The speeding proportion is more than 0.20. Okay. In this case, the police do not install speed controls and lives are put at risk. So potentially, when we make this type 2 error, we would make a decision to not put the speed controls in place, and that might endanger somebody's life. All right. Tomorrow's lesson, we will go through top to bottom everything, the conditions, everything you need to do for a hypothesis test, and we will be mostly through 9-2. Okay, once we get through the first hypothesis tests, the rest of the hypotheses just start rolling. We just figure out what's different about them. Okay, the hypothesis tests they start talking about on the chi-square tests, same kind of logic. Um, find enough information to either reject the null hypothesis or to fail to reject the null hypothesis. Other than that, it's all wording of answers. So once we get through a couple hypothesis tests, the rest of them will be very similar with just changes with formulas, changes in how we find the test statistic, but the logic behind um, rejecting and failing to reject, the logic behind those are basically all the same. So uh, yeah, that's it. Um, um, please tune in tomorrow to the AP lesson. Please also watch my video and look out for some more homework coming tomorrow. All right, that's it.